Welcome to our Vision Campus. Analyzing 2D images is very useful in many machine vision applications. However, sometimes it is necessary and helpful to create a 3D image of an object, such as in robotics, logistics applications, or autonomous vehicles. Today, various imaging techniques can provide 3D information for a machine vision application. Scanning techniques use a projected line of light onto a surface. A standard 2D camera captures many images of just the line while the object, camera, or light is in motion. Other techniques like stereo, structured light, and time of flight don't require scanning. In this video, I will introduce the basic operating principle of time of flight, or in short, TOF. I will highlight the advantages and disadvantages and show you some applications illustrating how time of flight can be used for machine vision. This is a fast, easy to install, simpler, and cost-effective technique. So let's get ready for the third dimension. A time-of-flight camera consists of the following main components: a lens, an integrated light source, a sensor that stores all capture image information, and an interface. This system is able to capture both depth and intensity information simultaneously for every pixel in the image. These cameras have great potential for machine vision applications because they natively capture the depth information that must be inferred by traditional imaging systems. Because the depth information is independent of the intensity and object color, you can separate the object from the background with relatively simple algorithms. Furthermore, its compact construction, ease of use, accuracy of about 1 centimeter, and high frame rates make TOF cameras an attractive solution for a wide range of applications. In easy terms, a time-of-flight camera works by first illuminating the scene with a pulsed or continuous wave light source and then observing the reflected light. Time-of-flight cameras based on the principle of pulsed light sources measure the time that it takes for a light pulse to travel from the emitter to the scene and then back after reflection. As the speed of the light is known, by using basic math, the distance to all of the points on the object surface can then be determined. Time of flight using continuous waves detects the phase shift of the reflected light. Modulating the amplitude creates a light source of a sinusoidal form with a known frequency. A detector determines the phase shift of the reflected light. And again, through simple math, a depth for each point in the scene can be easily calculated. No matter which principle you use, providing a light source capable of illuminating the entire scene makes it possible to determine the depth of all points in the scene with one shot. The result is a range map, where each pixel encodes the distance to the corresponding point in the scene. So what does a TOF image look like? This example shows the depth information as a pseudo-color image. Blue is far away and red is close. As the TOF camera captures a normal 2D intensity image in parallel with the depth information, we can merge the information sets and create a textured 3D graphic. Compared to other 3D measurement techniques, TOF offers advantages like high resolution and real-time capabilities. It can work in low light or even no light and creates only medium costs. Despite all these advantages, there are also some limitations that must be considered. Scattered light occurs due to unwanted reflections. Bright surfaces located very close to the camera quickly scatter too much light into the lens and create artifacts. The TOF distance measurement requires light that has been reflected just once. Light that is reflected multiple times distorts the measurement. Multiple reflections are typically produced by corners and concave shapes. Ambient light or environmental light, such as sunlight, make outdoor use difficult. The high intensity of sunlight causes a quick saturation of the sensor pixels. The actual reflected light from the light source cannot be detected. Multiple cameras can skew the measurement, because their individual light sources can disturb each other. Furthermore, depending on the manufacturer, the working range of TOF cameras can vary greatly. Also, the depth accuracy of this camera is still only around 1 centimeter in an optimal setup. But even then, there's no quicker way to capture 3D information. In logistics, for example, TOF cameras can be used for packaging assistance, box filling, stacking, volume scanning, or labeling. In robotics and factory automation, TOF cameras are used to find, pick, or mount objects. They easily detect damaged objects or stacking failures. In the medical field, TOF cameras play an important role in patient monitoring and patient positioning. For autonomous vehicles, these cameras are a valuable tool for navigation and safety warnings. All these applications prove that time-of-flight technology is revolutionizing the machine vision industry by providing 3D information. They are an attractive solution for a wide range of applications. Thanks for watching.